Hi, this is Edwin D'Souza, and this is going to be part two of homework 7, designing a design space explorer. So the best way to um, see how it works is review the code first and see how it works on each step. So this is my main file, um, and all the functions that I've written are in this particular file, extract attributes. So let's go through each of the steps. The first step is to extract and store the attributes in a list of lists, which basically is we read the lib_sobuild.info file, which gives us 5 different attributes, and within each attribute has different set of combinations. So the first attribute array could have the values ram, reg, or expand with array index is equal to const. Same applies for all of these. And what this basically does, this particular part of the code, this particular function, get attributes, um, it just extracts all of these and stores them in a list individually and stores those lists in another list called attributes. Okay, so for example, a list for the first attribute, the list would have 3 values, which would be array1 of array would have all these 3 values in them. The second list would have all these 4 values, and so on. And finally, all the lists that we individually created for each of the attributes is stored in a list itself. So that's why it's called a list of lists. All right. Now, using that list that we store in the variable attributes, we create all the possible combinations of the pragmas. And the way we achieve that is, let's see how we do that. But I'll give you an example so that it's easier. So let's look at, for example, each of these attributes. Now I'm going to bring in this particular thing. Okay, interesting. Okay, so the way I want to correlate this is think of a tree, and so we have A, B on the top, C, D on on depth. Let's say this is on depth 0, depth 1, depth 2, or depth 1, 2, 3, whatever, however you want to count. How are you going to correlate to this? Okay, so assume that in the actual Sobel file or Sobel.info file, we have 3 possible combinations for attribute 1. Okay, but in my case, let's make it simpler and say that assuming attribute 1 has 2 possible combinations, and that is A and B with values ram and reg. I've just assigned A and B for simplification. Let's say the next level corresponds to the next attribute, which is attribute 2, and it has 3 of them. So 3 of these. Okay, and the final, let's go to attribute 3, which has 2 possible combinations, E and F. All right, so now given this, what we can clearly make out is that each level of the depth corresponds to a, let's see how this works. Okay, okay, each depth value corresponds to the attributes, right? So this is attribute 1, this is attribute 2, this is attribute 3. And each unique node corresponds to the combinations of those attributes. So this is 2, and this has 3 unique nodes, so 3 attributes, and here there are 2. So 2 unique combinations belonging to attribute 3. Now the way it works is first in the code, as we can see, let's have a look. Let's look at the function for extracting the attributes. Um, First thing over here, which I initially forgot to mention, it calculates the total possible combinations, which is very simple, which is look at each of these attributes, how many attribute combinations are there, and multiply them with each other. So this is 3 times 4 times 4 times 2 times 2, which should be about 192 possible combinations. That's what the code initially figures out. And what we're essentially doing is creating a matrix which is of size, which has rows corresponding to the number of attributes. So in this case, there are 5 attributes, so there would be 5 rows. and columns that represents the total number of combinations, which is 192 combinations. And if you want to extract a unique combination, you just pull out a particular column. So if you take column 1, you get a unique set of attributes. So now given that, let's see how it works. So for example, in this code over here, we have the value iterations. Iterations refers to how many times do I have to repeat that particular attribute combination, not attribute combination, that particular, yeah, attribute combination in the matrix. So how many times do I have to repeat A before jumping to B? How many times, and repeating B again. It has also a certain number of repetitions. Usually the iterations, the repetitions with it are same for each node, or I should say A has the same number of iterations, B has the same number of iterations, if that makes sense. C has the same, D and G has the same. For every depth, they have the same number of iterations. And the way we determine that is we go from a bottom-top approach. Now, the reason why I used a tree to start off with is because you can find out, if you use a depth-first search algorithm, you can find out the unique combination. So ACE is a unique combination, ACF, ADE, ADF, AGE, and AGF. Okay, and you can apply the same thing for B. But another approach which I went through is looking at from the bottom top and treating each of these as a let's see, I hope cancel. Okay. Oh god. I hope that didn't cause anything. Okay, so we're back. Okay, it worked. Okay, so let's look at this right now. So for example, in attribute 3, for instance, I look at each of the attribute combination, which is E and F, right? And I ask myself, how many leaf nodes are here? In this case, this doesn't have any leaf nodes, so I'm going to put iterations as 1, which means that this will repeat once before jumping and repeating this one again, and so on. Now, you can go above for this and say C, for example, right? How many iterations, how many leaf nodes? Assuming this is the root node, how many leaf nodes does it go to? So that is, it is 2, right? So this will repeat itself 2 times before jumping to D, repeating itself 2 times, and jumping to G, repeating itself 2 times. Okay. Then I go to A. Now, how many leaf nodes does this correspond to? This is the tricky part. Okay, so it's actually 2, 4, 6 leaf nodes, because if you see, it goes, A goes here to here, and that's what you do. And so this will repeat 6 times, and so will this repeat 6 times. So that is what the iterations do. And what that allows us to do essentially is create a nice matrix. And like I said, if we're going from the bottom approach, let's see, for example, I do that, and where's my Excel sheet? Okay, let's say I do that. This was what happened. So like I said, like for example here, this is the bottom one, which has no leaf node, so it's 1. So it repeats once. So it repeats once, then repeats F once, E once, F once, so and so till all the possible combinations, right? Now, let's look at this layer, correct? How many combinations of C are there? So 1, 2, like I said, 2, because it corresponds to 2 leaf nodes. So 2, then jumps to D, 2, G, 2, and then again it resets and then starts from C again, C, D, G. And the same thing applies for A and B. All right, so that's how it works. Now let's look at the code again. This time let's look at the attributes. Let's look at the main. So now we've got the combination attribute, combination of pragmas, all the possible combination of pragmas. So I've got it, and I've got the combination value stored here, and then I convert it into a data frame. Now we want to extract the plot points, and how do we do this? Using the attributes, the combination attributes that we have in the matrix, we create unique header files. We keep creating header files. So the way it works is let's say there are 192 combinations of pragmas. Those combinations will be used to create a header file, and that header file will be used to run the code, will be used to parse and then synthesize BDL tran, C parse, whatever is that, using those particular combinations. And then it reads the QR file and extracts the ALUTs and the latency. So let's have a look at this particular function, which is extract plot point. So initially we know what the rows and columns are, which is basically all the combinations, and 2 because we're plotting x and y values, so that is it. And essentially this is the function that extracts the plot. So let's look at extract plot points. Let's scroll down. Okay, okay. So this part of the code basically, um, sorry, I think this opens the Sobel dot. If I'm okay, yeah, sorry. It creates a text file called attributes attrs .txt, and what it does is it writes the combination of pragmas, and then this part of the code changes it to a .h file, and then um, what we do is we run these lines of code on the terminal, which is cparse and then bdl tran to get the functional library units and the blib file. All right. Now, what does this allow us to do is to get the QR file. So then we have a function called extract points QR file, which is okay. And this is another function called extract points QR file, which extracts the points from the QR file. So we just created the QR file in the previous function. Now we extract the points. And basically we're reading the file, and as you can see here, it's at this point when we extracted all the ALUTs and the latency. All right. Then following that, once we get the plot points over here, this is to just save it in case if something goes wrong. This is not necessary, but this was just a safety precaution that I did. Now we can use that plot points to actually plot the area versus latency and get the Pareto optimal points. So this function does the plotting, and what it essentially does after that is it returns the optimal ALUTs and the optimal latencies. Okay. Now, which is I think here in the code itself. So let's see, where is the Pareto? Let's look at the Pareto optimal. Okay. So essentially these are the plot points, and what it does, it sorts the plot points against the latency. So it's sorting it with respect to the latency first, then it sorts with respect to the number of ALUTs. This part is just plotting. This whole thing is plotting till here. Over here, what we're doing is we're just storing the Pareto from the Pareto optimal, I believe from the Pareto points. We're extracting the optimal ALUTs and the latency. That's pretty much it, and then we return those values. Okay. Now after that, what we do is now that we have the optimal points latency, now we have to get the pragmas that correspond to that. The good thing is the points are stored in a manner that corresponds to the same matrix, that corresponds to the matrix of the combination. So I just have to get the position where the latency and the ALUTs are located. So let me give you an example. So here, for example, it shows you, let me show you an example. So let's see, let me see plot points. I think that file is good. Okay. So for example, plot points. Okay. Now it is stored in a manner that corresponds to it. So for example, this, right? So this corresponds to line 3, right? So line 3 basically means if it's stored in an array or something, it would be 2, right? So 2. So if I go to column 2 in my pragma combinations or my attribute combinations, uh, this ALUT and latency would correspond to it. So basically, I just need the position of where uh, the optimal ALUTs and latency takes place. I extract the position, which basically is the line position -1, and I can use that and find the combination pragmas in. I can find those particular set of combinations corresponding to. I can find the pragmas. Now, what was it? Yeah, I can find the pragma combination that corresponds to this particular position. Uh, and that's how it works. So let's have a look at this. It's the same, yep. And then once those are extracted, it is printed out. It's also saved to a .csv file, and which is a good thing, so that you can review it and see how it is in order to make observations or inferences. And yeah, that's pretty much it. That is the design space. And this is a test output just showing you how it runs. It tells me this is the iteration, which iteration of the combination is it. So this is at the last combination at the end. Gives me the Pareto optimal design. So there are two of them with 176, 175 ALTs and latency of 1. And this is basically printing for pragma combinations of 176 and 1 and 175 and 1, essentially. Yep. So yeah, that's pretty much it for this. Also, I can show you the plot. It saves the plot as a picture. So this is what you get. And this is where all the plot points are located, where all the optimal plot points are located, which is about 32 of them, 16 corresponding to ALUTs of 16 and latency of 1, and another 16 corresponding to ALUTs of 16 of no, sorry, let me repeat that again. So 16 plot points here uh, corresponding to ALUTs of 175 and latency of 1, and 16 plot points corresponding to number of ALUTs of 176 and latency of 1. All right, and that's pretty much it. That represents the code and how it is run. Um, thank you.